Well, hello there. This is Mrs. Sharp, and today we're going to go over some notes on 5.2. In this learning target, we would like for you to be able to explain different characteristics for ionic and covalent bonds, including some of these terms. So for ionic bonds, we want you to be able to talk about things like what are monatomic ions, what are polyatomic ions, what is lattice energy, what is the melting point like for ionic bonds? What is the conductivity of heat and electricity like for ionic bonds? And what is the solubility in water like for ionic bonds? For covalent bonds, we want you to be able to talk about the melting point, the solubility, the conductivity, and bond lengths and strengths, and how those two things are related. So let's get going. First, let's talk about ions. An ion is when a neutral atom or a group of neutral atoms gains or loses electrons. So first, let's talk about what happens when an atom gains an electron. When an atom gains an electron, it is going to become negatively charged, and that's known as an anion. When an atom or a group of neutral atoms loses electrons, it's going to have an overabundance of positive charge, and that's known as a cation. Now, when something that is just one single neutral atom does this, that's known as a monatomic ion. Monatomic means a one-atomed ion. When it's a group of neutral atoms, that is known as a polyatomic ion. Poly means many. So we have monatomic ions and polyatomic ions. Now, monatomic ions are what we've talked about so far, such as when you have strontium, for example, it has 2 valence electrons, and it'd be most likely to lose those 2 valence electrons to show the octet rule. So a monatomic ion, there's just one atom that has lost electrons, it's strontium. But a polyatomic ion has a group of atoms joined together that gain or lose electrons. And examples of these are on the back of your periodic table. And there's a table that says Table of Polyatomic Ions, and most of them are anions, and you have just a couple of cations. But an example of that might be phosphate, which is PO4 minus 3. So phosphate is actually 5 atoms, 1 P and 4 O's, all bonded together. In fact, they're 2 nonmetals, so they'd be covalently bonded together. And the whole blob has gained 3 extra electrons than it would have normally. So we just talked about strontium as being an example. Other examples might be something like sulfur, which has 6 valence electrons. It would pick up 2, so become sulfur negative 2. Potassium has just 1 valence electron, which it would lose, so become potassium plus 1. Fluorine has 7 valence electrons, so it would be likely to pick up just 1 more and become negative 1. So all of those are single atoms that have become ions. So single atoms gaining or losing electrons. So polyatomic ions are many atoms covalently bonded together as a group that have picked up a charge, either by gaining or losing electrons. So first on the left here, you have H3O+, and again, if you flip over onto the back of your periodic table, you would see this on your list of polyatomic ions as hydronium. It's one of just 2 polyatomic cations. In fact, it's the last one listed in your table. So the O's and the H's stay together and have an overall charge of plus 1. And then here on the right, you have S2O3. Again, S and O are both nonmetals, so they would be forming a covalent bond in between the S's and the O's, but they've picked up 2 extra electrons as a group, and that's why I'm showing them in this little bubble, because the charge goes for the whole group. So they stick together inside of the bubble, but the bubble itself has a negative 2 charge. That's thiosulfate, S2O3. Okay, let's talk about how you'd know something was ionically bonded together just by its physical or chemical properties. So one thing about ionic compounds is that they're usually solids that are hard and brittle at room temperature. Going along with this, if they're solids, that means they're going to have high melting and boiling points. If you were to try to take an ionic compound that's a solid at room temperature, you would really have to torch it a lot to get it to liquefy. Ionic compounds don't conduct electricity as a solid, but if you melt them or you dissolve them in a liquid, like water, they do conduct electricity. That term is called electrolytic, or they are known as electrolytes, if they can do this. Now, ionic compounds are not always soluble in water, but they are more likely to be soluble in water. And they form a highly organized pattern called a crystal lattice. It has a three-dimensional crystal lattice structure, and the smallest repeating chunk in that crystal lattice is known as a formula unit. Lattice energy goes along with this crystal lattice idea. As you guys can see, I have some green ions, some cations, sodium +1, and some yellow, chlorine -1 anions. And we can see that those are attracted together. And in fact, that dotted line right there is your ionic bond between those different ions. The thing that happens in an ionic compound, however, is that you have tons and tons and tons of ions. And so if you were to have, for example, one formula unit right here, one Na and one Cl, because that's how we would write it, that's going to repeat over and over and over again, and they're going to line up in a very specific way. For example, if this Cl -1 right here is oriented against this formula unit right here, they would flip around so that the chlorine and the Na+1 form another ionic bond in between the two of them right there. And that another formula unit coming in would flip itself around, so they're attracting there. And so on and so forth until you have a three-dimensional crystal structure where all the Cl -1s are surrounded by Na+1s and vice versa. So all of these right here are ionic bonds because they're between two oppositely charged ions. Now, if you were to try to separate all of those, break every single one of those attractions, that would be known as the lattice energy. So it's the energy required to separate 1 mole of the ions in the crystal lattice structure of an ionic compound. So it's always going to require energy to do that. It's going to separate those, pull them all apart. Now, some things take more energy to do that than others. For example, smaller ions can get closer together. Because they can cozy up next to each other really, really close, it's harder to separate them because their charges are closer together. Just like putting two magnets really close together would be harder to separate than those magnets not being close together. So smaller ions have a higher lattice energy. Bigger ions can't cozy up quite as close to each other, so it's a lot easier to pull them apart, and they would have a smaller or a lower lattice energy. Let's switch gears and talk about some covalent bonds. Covalently bonded compounds can be solids, liquids, or gases at room temperature, and they don't conduct electricity very well, either just on their own or when they get dissolved into water or liquefied. They usually have lower melting and boiling points than ionic compounds, and they can be soluble in water, but not generally to the extent as ionic compounds are. There are 3 types of covalent bonds that can be formed between two atoms. The first is a single bond, which is sharing a single pair of electrons. Then we have a double bond, where 2 pairs are shared, as you can see with the 2 oxygen atoms together, a total of 4 electrons being shared. And then finally, the nitrogen atoms at the bottom are showing a triple covalent bond, where 3 pairs of electrons would be shared between atoms. The bond dissociation energy is a term we've talked about before, and that's the amount of energy required to break a bond. And the bond length is the distance between the nuclei of 2 atoms sharing electrons. So it turns out that triple bonds have the highest energy to break. So triple bonds have the highest bond dissociation energy, but they have the shortest bond length, and that's because to share so many electrons, they have to get pretty close to each other. On the other hand then, single covalent bonds do not take as much energy to break, so they have a lower bond dissociation energy, and they also have a longer bond length because they don't have to get quite as close in order to share just the single pair of electrons. So bond dissociation energy and bond length are inversely related. Here's a summary of the differences and similarities between ionic and covalent bonds. I'm leaving you with this if you would like to copy it down. Have a great night, and I will talk to you soon. Bye!